In our previous video, we looked at isoelectronic structures, isotones, and isobars of an atom. In this video, we want to focus on mass defect of an atom. But to start with, can we quickly think about the English word defect? When there is a defect in something, it means there is a lack in that thing. Something is lacking. That thing is not complete as it should be. That's what defect is. And so we can actually link it to the mass of an atom. Talking about the mass of an atom, it has a mass number, the nuclear number. Alright? That number that you obtain when you add proton towards neutron in the nucleus of an atom. We usually represent the mass number as capital letter A, is not so. So for an atom, when you observe the mass of that atom, and you calculate the mass of that atom, it has been observed that these two masses are not exactly equal. The actual mass of the atom, that is the actual mass number, also known as the actual nuclear number. You can also call it the observed mass number or the observed nuclear number. It is obtained from a mass spectrometer. The instrument used in measuring it is mass spectrometer. That mass that is observed of an atom is not equal to the mass calculated when you consider the proton number, the neutron number, and the masses of proton and neutron. Because of course, the nuclear particles, proton and neutron, we can use the number of proton, the number of neutron, the mass of proton, the mass of neutron, to actually calculate the mass number, the nuclear number of an atom. When you do that calculation and you obtain the mass number and then you compare to the mass number, the mass number that is measured using spectrometer, these masses, two of them are not equal. And that is the concept of mass defect. It was observed with helium before. So by definition, mass defect is simply the difference between the observed mass as obtained from mass spectrometer measurement and the calculated mass as obtained from the mass of proton and neutron and the numbers of proton and neutron. Simply the difference between the observed mass and what the calculated mass gives us what we call the mass defect. We use change in n to represent mass defect, and by definition these are the key words. Okay, mass defect is difference between observed mass and what calculated mass of an atom. According to Einstein's theory of special relativity, there is this relationship between mass and energy. In fact, given by this equation 3, the Einstein's energy is giving us mass defect times square of speed of light. And you know speed of light is 3 times 10 raised to the power 8 meters per second. It is possible for this mass to be converted to energy. And that tells us that mass defect in a way is also related to energy. Yes, the energy that is given off, that is liberated when protons and neutrons in the nucleus of an atom combine to give us the nucleus. Of course, you know we cannot be talking about the nucleus of an atom without the mass and the neutron of that atom, because the proton and the proton and the neutron of the atom, these two particles make up what we call the nuclear particle. They make up the nucleus. So that energy that is given off when these two particles, proton and neutrons, combine to give us the nucleus of an atom is also known as the mass defect. It's related to the mass defect. Mathematically, our mass defect is giving us calculated mass, which we're using Cm for it, minus actual mass or observed mass, which we're using Am for it. You need to have these formulas at hand. Is that okay for calculation purposes? Now, how do we get a calculated mass? You know that the actual mass is obtained from spectrometer. So it's a standard measured from an equipment, an instrument. But the calculated mass requires mass of proton and the number of protons, mass of neutron and the number of neutrons. So we need to get a calculated mass, and this is the formula for it. Mass of proton times the number of proton added to mass of neutron times the number of what? Neutron. In a situation where question is given to you in exam, the mass of protons will be given, the mass of neutrons will be given. The number of protons and neutrons may not be given. You can find it out. We discussed that in our previous class already. Proton number is equal to atomic number. And once you know the atomic number and mass number of an atom, you can get a neutron number by doing mass number minus proton number, giving you what? Neutron number. The definition of the terms we use in this formula are written here on the board. So you can go through them. In the next video, we're going to take a question and see how we apply these formulas that we have on the board. On the board here, we have a question. I'd like us to look at the question and solve it together, okay? It's a simple one on mass defect. We have to calculate the mass defect of neon, given that the mass of neon from mass spectrometer measurement is 20.183. Alright, take the masses of proton, neutron, and electron as 1.0075, 1.0089, and 0.006 respectively, relative to carbon 12. Now the masses given to us here with the word respectively shows that the first number goes with the first item here, proton, the next number goes with the second item, the particle neutron, and then the next one goes with electron. Is that okay? Now in solving this problem, I decided to bring out the data, the information that we know from the question already. We know that the atom is neon, right? And from knowing the atom to be neon, we can determine the number of proton. Of course, neon is atomic number 10. This number is equal to the proton number. In our previous class, we stated that atomic number, which is this, we use Z to represent it, right? It's equal to the number of what? Protons. So from there, let's add up other information we know. Number of proton is equal to atomic number, which is 10. Is that okay? We know the mass of proton already given to us. We can also calculate the number of neutron. To get the number of neutron is equal to this mass number. This mass number here, 21. Please take note, it is not the actual mass measured from mass spectrometer. It is not even the mass calculated from that calculated mass formula. It is the mass called the rounded off mass. After obtaining this value from their relative atomic mass calculation from isotopic value, it's usually rounded off. Is that okay? So we call it the rounded off mass. We're going to do 21 minus 10 to get the neutron number. So 21 minus 10, and that is going to give us 11. Am I right? Good. 21 minus 10 is 11. These are the things we need for a calculation. You know that mass defect, recall, by formula, mass defect change in M is equal to calculated mass minus what? Actual mass, also known as observed mass. Now we know our actual mass 20.183. We do not know calculated mass. So I will write that, but calculated mass, you see something here, right? Directly what we're asked to calculate is mass defect. So I had to write out the formula. Writing out the formula, the next thing is to substitute the values there, put in the value of calculated mass, put in the value of actual mass. But I observed that from here, I only know actual mass. I don't know calculated mass. So in order to calculate our mass defect, I need to find out the value of calculated mass first. And that is why I have to recall the formula for calculated mass. Suppose in the question, actual mass from mass spectrometer is given and then calculated mass is also given. You just substitute them directly and get a result. Alright, we don't know calculated mass. Let's find it out. It's equal to mass of proton times number of what? Proton. Add it to what? Mass of neutron times number of neutron. Okay, so number of proton, number of neutron. Alright, so this is the formula, we know that, isn't it? Now the formula. Good. We can now solve for calculated mass. Mass of proton from the question is 1.0075, is that not so? And then we multiply by number of protons, so 1.0075. We're going to multiply it by number of proton. The number of proton is 10, that's the atomic number. We're going to add this value to mass of neutron. Mass of neutron from the question, the data given to us is 1.0089. We'll multiply that by number of neutron, which has been calculated to be 11. So our calculated mass here will be equal to what we got to reach out for our calculator now, okay? So I'm going ahead with my calculator. I hope you have yours, so you can press yours. Let's see, 1.0 10.075 multiplied by 10 is giving me 10.75. Okay, 10.075 plus, then you need to be done with the bracket first, multiplication first. Remember the order of coordinates. Then 1.0089, we're going to multiply it by 11, and from here it's giving me 11.00979. So if you add up this, calculated mass is going to give us 21.1729. Okay, 1729. We can approximate this to 21.173, being that the actual mass we need for this calculation is in 3 decimal. We want to approximate this to 3 decimal. Our problem is solved, you know. All we need to do now is to go to the mass defect formula, which is calculated mass minus actual mass. The calculated mass is 21.173 minus actual mass is 20.183. It's important for us to know that usually the calculated mass is greater than the actual mass. Is that okay? So don't forget that. In case of a question, which of the following is correct? Question like that. The calculated mass is always greater than the actual mass. The mass defect here is not going to be, so I'll subtract 20.183 from it, and that's giving us 0.9899. Is that okay? So this is the mass defect. You see, it's possible for us to convert this mass to energy using the Einstein's energy equation. All we need to do is to multiply this by the square of 3 times 10 raised to the power 8. That's the speed of light. Anyway, for this question, this is the answer. In our previous video, when we discussed mass defect, it was stated that using Einstein's theory of special relativity, it's possible to convert mass defect to what? Energy. And that we actually stated that the energy liberated in holding the nuclear particles, that is protons and neutrons together, is related to its mass defect. So what does that tell us? That we can actually relate mass defect to energy. And that brings in the concept of binding energy. Bind. We want to look at that word from the term bind. To bind means to hold together. Is that okay? Which therefore means that the binding energy is an energy related to holding something together. And what are the things? The nuclear particles. What are our nuclear particles? You still remember that, right? Can we mention that? Our nuclear particles are the particles found inside the word nucleus of an atom. And they include proton and neutrons. So the energy required to hold these nuclear particles together is actually referred to as binding energy. By definition on the board here, we have binding energy as the energy equivalent of a mass defect divided by the mass number of that atom. The mass number in this case is the same as the rounded off mass. That mass number that we use capital letter A to represent, you would recall when we represented an atom with X, we had capital letter A like this, we had Z this way. Is that okay? So the number you usually see written on top of an atom here is called the rounded off mass. So if you use the word mass number straight, you are actually referring to the rounded off mass. So the energy, which is equal to mass defect of an atom divided by its rounded off mass, divided by its mass number, divided by its nucleon number, is what we call binding energy. Mass number, rounded off mass, nucleon number, they mean the same thing. Because binding energy is energy that is related to binding, holding things together, we can actually define it as the energy that is required to hold the nuclear particles together, the protons and the neutrons. And if that is the case, the energy required to hold something equals the energy required to break that thing. Hence, we can also say that binding energy is the energy that we require to separate the nuclear particles into their components, that is, into proton and neutron. Having defined the term binding energy, and you see that all through the definition, there is a concept of binding energy being responsible for holding the nucleon of an atom together. It therefore means that the relative stability of the nucleus of an atom can actually be estimated from the binding energy of that atom. In your higher chemistry, of course, we're going to treat that. Is that okay? Where we talk about the concept of the Magellan constant. That is not the focus of this course. Now, when you get there, you will cross it. Mathematically, binding energy is equal to the mass defect divided by the mass number divided by the rounded off mass. I'm using capital A here to represent the mass number. Is that okay? So that's the formula for binding energy. Take note of that. You're expected to have it at heart. There are certain conversion factors we want to be used to. 1 eV, this eV means electron volt. 1 electron volt is equivalent to an energy of 1.6 times 10 raised to the power minus 19 joules. Then when talking about mass conversion to energy, it's important for us to know that 1 gram is equivalent to a binding energy of 9 times 10 raised to the power 13 joules. In the next video, we're going to take a question to apply this formula of binding energy. Now we have this question I want to look at. Alright, it's on binding energy. I invite you to join me as we work on this question together. It reads, the exact mass of copper is 63.550 grams per mole. Exact mass, that is the actual mass. Alright, the observed mass as obtained from mass spectrometer measurement. Take note of that. The masses of proton, neutron, and electrons are 1.0075 grams per mole, 1.0089 grams per mole, and 0.006 grams per mole, respectively. The question requires that we calculate the binding energy in SI units per nucleon for which atom? Copper 64. Now, how do we solve this problem? First of all, we need to identify that the atom that this question is based on is copper, with the rounded off mass value there of 64. So we know the value of A, capital letter A, the denominator for binding energy. Now, if we are to calculate binding energy according to the question here, we need to remember the formula for binding energy first. Binding energy is mass defect divided by what? Mass number. And then the mass defect, we know it is calculated mass minus what? Actual mass divided by that mass number here to get your binding energy. The numerator, calculated mass minus actual mass, gives us the mass defect. Now, if you look at this, from the data presented to us, we know the denominator A is equal to 64. That is the rounded off mass of copper. You follow me? Alright, now did you take note also that we know the actual mass? The actual mass of copper is the exact mass given to us from the question, 63.550 grams per mole. That last zero is insignificant. If I don't want to use it, I can just put it off, since it is 0 as the last digit of the decimal part. Now, you would agree with me that to calculate binding energy here, this is the formula already. We know the denominator, we know the actual mass, we do not know the calculated mass. Which means, to obtain the binding energy, I have to solve for the calculated mass first. But we know that calculated mass is equal to mass of proton times number of proton. It's going to be added to mass of neutron times number of neutron. So again, look at this. We need the number of proton. We need the number of neutron. We know their mass numbers, the mass of proton and the mass of neutron. They are given to us. This proton mass and this mass of neutron. We don't need the mass of electron. Take note. Electron has no place in this calculation. So we can actually obtain the number of proton. Number of proton for copper is equal to the atomic number, we know that, so it's 29. And then we can obtain the number of neutron. Number of neutron for copper is the rounded off mass, alright, the mass number minus the atomic number. And so if you do 64 minus 29, this should give us what? 35. So there are 35 neutrons in copper 64. It implies that the calculated mass will now be equal to, if you work at that, let's see what we'll get. The mass of proton is 1.0075. We're going to multiply by number of proton, which is 29. Then add it to mass of electron, right? Mass of neutrons. Add it to mass of neutrons, which is 1.0089. Then multiply by number of neutron, which is 35, as we obtained for copper. Calculated mass, if you work out this, is that okay? It's going to give us 64.529 grams per mole. Did you take note that the calculated mass is still greater than the what? Actual mass, as expected. I stated that under mass defect, the calculated mass is usually greater than the observed or actual mass. Alright students, we are now set to calculate the binding energy. So binding energy will now be equal to, I have to use this formula now. Calculated mass is 64.529 minus the actual mass is 63.550. I'm going to divide this by 64, the rounded off mass. If you work on the numerator, 64.529, then subtract 63.55, it's going to give us 0.9979 divided by 64. So you take note of something, that the numerator, which is mass defect, is 0.979. So suppose the question asks us to find mass defect alone here, this will be the value in grams per mole because the masses are given in grams per mole there. Can we now obtain the binding energy by dividing that 0.979 by 64? So that will be divided by 64, and from here it's giving me 0.0153. Alright, it's going to be in grams per mole. Let me put this in standard form so I can say or in standard form, this is 1.53 times 10 raised to the power minus 2 grams per mole. How did I get this? I moved the points 2 times. If you want to write in standard form, you need the first non-zero digits, which must be between 1 and 9. I get it, let's say 0 and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? The first non-zero digits between that value. And here it is 1. So you move your point 2 times. So it will come between 1 and 5, 3. Now since you moved your point 2 times to the right, you multiply by 10 raised to the power minus to the number of times you moved your point. Is that okay? Now we've obtained the binding energy in the unit of grams per mole. Remember that the question said we should get a value in what? In SI units. So I'm going to write in SI units. Recall, we know the conversion factor that 1 gram, or you say 1 grams per mole, is equal to 9 times 10 raised to the power what? Okay, that's 13 joules. Is that okay? Therefore, it means that, or it implies that 1.53 times 10 raised to the power minus 2 grams will now be equivalent to, now to convert from the grams per mole value to SI unit joule of energy, simply multiply the mass you obtained in terms of the binding energy by this conversion factor 9 times 10 raised to the power 13. So this will give us 1.53 times 10 raised to the power minus 2. The gram will cancel out from here. So you multiply it by 9 times 10 raised to the power 13 joules. So you now obtain that the binding energy will be equal if you multiply this. Okay, let's see how it goes. 1.53, let me multiply the numbers without powers first. 1.53, I'm going to multiply it by 9. So this is giving me 13.77 times 10 raised to the power. Come to this 10 raised to the power minus 2, 10 raised to the power 13. Pick one of the 10 and add their powers. Minus 2 plus 13 is going to give us positive 11 joules. And this can still be written. Remember I told you something about standard form, that you need the first non-zero digit to be only 1 digit number. So it means I'm going to move these points to between 1 and 3. Is that okay? So moving it one time to the left, that will give us 1.377, then times 10 raised to the power. This time around, you moved the point to the left once. So this is 10 raised to the power 11. You now need to add one time you move the point, because you move to the left, you add. You're going to get 12 joules here. So this is the binding energy in SI units. In the next video, we're going to introduce the concept of packing fraction. Packing fraction is the next thing we want to look at. For an atom, the packing fraction actually is a measure of either the gain or the loss in total mass when these nuclear particles come together to form the nucleus. Mathematically, we can define it as a relative difference between the actual mass and the rounded off nuclear mass. Relative difference between actual mass. It's going to be actual mass minus rounded off mass divided by rounded off mass, because we're talking about a relative difference. Mathematically, in terms of the formula, once again, the packing fraction can be expressed as what you see on the board here. So that's the formula which, of course, you're expected to have at heart. We've got this question on the board here. We want to determine the packing fraction of iron 56 if the observed mass from the mass spectrometer is 55.847. Solution. So from the question, we know that we are dealing with iron 56. So I have 26 iron. And then Looking at the question, the actual mass was given to us to be 55.847. The rounded off mass here is the mass number of iron, which is 56. So you need to recall that packing fraction is equal to actual mass minus rounded off mass divided by rounded off mass. So what's going to be the packing fraction? So we're going to substitute there. You have the relative difference formula here. So actual mass is 55.847. It's going to be minus 56 divided by 56. Working around this, let's see what the packing fraction would be. So it's going to give us minus 0.0027273. In standard form, we can say that packing fraction is equal to, you know I told you about standard form, you move your point so that you have a one non-zero digit number. Then you have your point and other decimal if they appear. So I'm going to move my point from here 1, 2, and 3 to locate that first non-zero digit, which is 2.73. This is minus, you know. If you subtract, do the subtraction of the numerator, you're going to get it minus. Because this is 55 points, it's less than 56. Alright, so times 10 raised to power. I moved the point 3 times to the right. If you move it to the right, you subtract from the power of 10. Originally, this does not have time, or even if you multiply by 10, this thing standing alone like this is times 10 raised to power 0. Because 10 raised to power 0 is 1. 1 times this still maintains that value. So times 10 raised to power 0, if you minus the 3 times you move the point to the right, you get 0 minus 3, which will give us minus 3. So that is the packing fraction. Please take note, packing fraction has no units. In our next class, we are going to deal with development of atomic theory.